Okay, so welcome to Eric Severson's PhD exit seminar. Eric has been my student for, is it 3 years now? I think 3 years is about right. He took my class on molecular computation, and by about halfway through the term was just kind of walking back to my office with me, asking me a bunch of questions about various problems I'd put out, solving them, solving new problems I didn't assign. At some point, getting so far into a solution that it became his first paper. And yeah, since then has, just been pretty exemplary. And I mean, it's been pretty, it's been pretty long since I felt like I'm teaching Eric a lot. It's more like I felt like I'm the student and he's, he's the teacher here. Certainly on a lot of papers we're doing, I mean, he's just brought stuff to the table that, I wouldn't have known how to do, just probability. And so anyway, this seminar is going to showcase just about everything he's done, and it, runs the gamut over a lot of stuff I'm interested in, but all of it has to do, with, chemical computation and distributed computing. So thank you for joining.
Thank you. And thank you everyone for being here. Okay, so there's a big old, maybe scary sounding title, Advances in Discrete Chemical Computation. And really, I'm just going to start with this bottom word here, population protocols. This is really the model, as I'm going to phrase it, that we're going to focus on. So let's try to see what this is if you've never seen it before. So this originally came from the distributed computing community, and the model itself is pretty simple. So it describes a population of agents who have random pairwise interactions. So as a really simple example here, we have agents that only have two states, call them I and S. Here we have a population of 5 agents, and randomly pairs of them are going to interact. And if a pair of them interacts, we need to know what to do. So there's going to be some transition function that describes how they're going to update their states. So in this case, if an I meets an S, they both become I. Otherwise, nothing happens. So in this case, nothing happens, but then an I meets an S, they both become I, and so on. So what does this describe? Well, this can be a model of many things because it's sort of so simple and universal in a lot of ways. A really important one is chemical reactions. So we could think about this as molecules bumping into each other. And this exact rule would be an example of what they call an autocatalytic reaction. But this could also be a model of social dynamics. So in this case, this could be a model of a very simple epidemic where I is infected and they're infecting the susceptible. And actually, the original paper was thinking about this as a model of wireless sensor networks. So in this case, we could view this as a gossip protocol, where the purpose is we're trying to spread information around the population. But more mathematically, a rule like this is going to give us some random dynamics. So more formally, that's going to be a discrete Markov chain. So in like a very simple example here with only 5 agents, I can just draw the entire chain. So each of these circles right here is one of the configurations. And then from each configuration, we can either move forward, infect another agent, or have a null reaction where we have no infection. And then eventually we'll reach the all infected state. So then we can also simulate this. So this is n equals 5, but then here's n equals 50. Here's an example of the epidemic spreading. So we start with a single infected, we eventually reach all agents infected. And as far as the time scale in which this goes, the notion of time in this model is to say every n interactions is 1 time step. So after 1 time step, after 50 interactions, we've infected a couple agents. And then if we look at a bigger population, so here we now have 5 billion agents, we can sort of see this very defined curve. And this is sort of exactly the well-known logistic curve, if you've ever heard of that. And it's also worth noting here that this is 20 units of time, but 20 units of time is about 100 billion interactions. And also this simulation took only 2 seconds to run. So I'll mention in just a minute some work on the software that actually made this plot. And this exact rule here, based on this exponential growth and exponential decay, you can show it takes log n time to converge. So that's actually pretty quick. And another thing you can actually see is log n time is actually how long it also takes for every agent to just have 1 interaction. So log time is fast, and it's also like the fastest you can hope to do anything in this model. So this fundamental process actually turns out to be really important for lots of other protocols. But the other main thing worth emphasizing in this model is the approach we take. So it comes from distributed computing, where the focus, as you might expect, is on computation. So really, you can think about it as in general, agents using their local interactions to compute some global property of the configuration. And one example that we'll talk about a lot today is majority consensus. So here's the simplest rule of trying to solve the majority problem. So let's initially imagine we have 55A, 45B, some population of A's and B's. And we would like to learn what's the majority. And here's a really simple way to do it. And I can sort of tell a story of this as some sort of a voting majority protocol, where initially we have A opinions and B opinions. And if an A meets a B, they're both going to become undecided. They're going to be U. And then both the A's and the B's, they're opinionated. So they're going to convince the undecided agents to adopt their same opinion. And again, we can simulate this rule. And initially with all A's and B's, we get a bunch of undecideds. But then because there's more A's, there's sort of a positive feedback, and we eventually get all A consensus. And it turns out actually this exact rule appears in real biological systems. So it's because it's so simple and ubiquitous, it actually does end up sort of getting selected by nature in some way. Now, as far as implementing population protocols, a very strong recent motivation has come from a new technology called DNA strand displacement, pioneered by some members of the audience right here. And for a very sort of simple description cartoon, here's a nice animation showing how an A plus B goes to C reaction gets implemented in DNA. So here we have a molecule that's representing A, a molecule that's representing B. They both bind to some third structure, and that's going to kick off this molecule that represents C. And it's been shown experimentally that sort of any arbitrary set of reactions could get simulated. So we can sort of view chemical reaction networks as a programming language. And that's one of the strong motivations for this model, for asking these sort of questions. What could this model compute? So in this work, we're going to talk a lot about what this model can compute, but we're actually going to start with a simulator package that I built, which is joint work with David Doty, which simulates this model. So this is called ppsim, and the package is here on GitHub. And it's a package written in Python that was designed to run easily in a Jupyter notebook. So you can install it with this one line, pip install ppsim. Then you're going to bring in this package simulation. So the simulation class is going to be the main workhorse. And let's simulate that approximate majority rule. So we're going to define 3 states. We have A, B, U. So our states are these strings. And if A meets a B, they both become U. And if A meets U, they both become A. So we have the 3 rules here. And then we're going to define a configuration, which is going to have a billion agents with 50.1% A and 49.9% B. And then we're going to create a simulation. And crucially, it has a very fast simulation backend. So it's written in Python like this, but then when we call sim.run, it's going to run really fast. So in this case, we went for 20 units of parallel time. It took a little over a second. And crucially, this number here is saying that it was able to simulate about 10 time units, which is 10 billion interactions per second. And then after it does that, it provides easy visualization. So then we can say, all right, I want to go sim.history.plot, and then we can get one of these plots. So here's that same approximate majority rule on a much bigger scale. You can see A taking over because it started with a significant initial majority. Also, there's very concise code you can use to describe protocols. So if you're thinking about something from the population protocols model, you tend to get some pretty complicated protocols. So here's an example, actually relatively simple one from the literature. Here they're describing the memory of an agent. So their agents have 5 different fields: role, flip bit, marker. Exactly what it does doesn't really matter. But the point is we can sort of take this description and then make an agent class in Python. So we're going to define a class called agent that has all the right memory structure. And then this paper had some pseudocode describing a transition, saying, all right, 2 agents meet, here's what they do. If the phase is marking, do this. If the phase is tournament, does that. And it's really get one-to-one to map this pseudocode over to real Python code that really describes the transition function. So it does a good job of sort of making your work and making your idea for a protocol sort of very easy to see, very open source, but also rigorously defined. This is real code. Another strong application for this package is in simulating chemical reaction networks. So this population protocol model is very related to chemical reaction networks, but moreover, we can actually handle sort of more arbitrary, more detailed chemical reaction networks. So here's sort of an arbitrary version of something we could simulate, which includes both unimolecular, so 1-to-1, and bimolecular, 2-to-2 reactions, as well as arbitrary reaction rates. So here we have different rates for how fast these reactions are going to run. There's a syntax we developed that lets you directly encode this as a CRN. And then once you give a CRN, it's able to simulate the exact distribution that would come from the existing CRN stochastic algorithm. So that comes from Gillespie, and it's called the chemical master equation. So we're able to sample the exact same distribution and confirm that. Here's a plot sort of directly comparing a CRN simulator, just confirming, yeah, we are sampling the exact same thing. So the distribution you would get is the same, but we're a lot faster. So there's asymptotic gains in efficiency from the simulator. And here's a plot showing that. So this is that same approximate majority rule. And we ran that rule for a range of population sizes all the way from 100 up to 1 trillion. And then on the left here, we have runtime. So here we have that 1 billion agents that we ran. That was taking about a second. But these other simulators are taking about 1,000 seconds. And if we had tried to go much higher, it would take very long to wait for these ones to finish. And the reason for that is because internally it runs this new multi-batch algorithm coming from Petra in the audience and some of her co-authors. And this algorithm is able to simulate order of squared event interactions in a single batch. And because of that parallelism, we get asymptotic gains. And that's reflected here in the plot. So the fact that these two lines have slope 1, that's showing that they're scaling linearly in their runtime with the population size. Whereas this slope of 1/2 is reflecting the fact that it scales like squared event. So this asymptotic gain is going to eventually take over, and it's going to make it much, much faster if you want to run very large population sizes. Then the next work I'm going to talk about is our first sort of theoretical result. And this is talking about that majority problem we've already mentioned. And this is joint work with Dave Doty, Masa Eftekhari, Leszek Senek, Grigor Shkawik, and Przemek Uznansky. So the exact majority problem is a bit stricter than what happened in this first protocol. So this approximate majority protocol is approximate. So it will often give you the majority, but there's no guarantee. So here's another simulation with the same initial configuration where B happens to take over. Sort of the random fluctuations push the count of B higher, and then it takes over. So this can fail. So when we talk about the exact majority problem, we want to get the majority correct no matter what with probability 1. Turns out you can do that with only 4 states. So here's the simple 4-state rule as a first example. So we again have states A, B. We also have lowercase a, lowercase b, where the intuition here is the initial states are capital A, capital B, and we're going to think about those as active. So these are the active opinionated agents. And when 2 differing active agents meet, they're both beginning on passive. And then the active agents are going to convert the passive agents to have their same opinion. So then how does this work? Well, the crucial reason this works now is the difference between counts of active agents is preserved. It never changes. So if we look at a simulation with 50,000 and 50,001 agents, this count difference of 1 is preserved all the way until the counts of A's and B's gets all the way down until we eventually remove the last B. And once you remove the last B, the last A is able to directly interact with the rest of the population and convert all the little b's to little a's. Unfortunately, this is really slow. So this sort of gap of 1 is the worst case. And when this gap is 1, the amount of time it takes is linear. So now in parallel time, this is linear. This is 100,000 agents. 100,000 times, very, very long. So this is sort of prohibitively slow. But we can solve the exact majority problem much faster. It's just going to take more states. And provably, you need more states. But if you're willing to use a lot of states, a lot of memory, there's actually another really simple algorithm. And the idea is to map the states to integers. So we have here in this example, we have 51 A's and 50 B's. And we're going to map A to some big integer, so here 202, and B to some negative integer, negative 202. And the idea is we're going to update by averaging. So whenever 2 agents meet, they're going to average their 2 integers, but they have to be integers. So it's going to be this discrete average. We take the floor and the ceiling. Or you can think about this as sort of passing some tokens back and forth, where the total number of tokens gets preserved. And then the output of an agent is the sign of their state. So if we let this rule run, the averaging rule will keep going, and then pretty quickly, they're all going to become blue. And the reason for that is you can actually prove that this rule is going to reach 3 consecutive values. So here we have 1, 2, and 3 in only log n time. And again, log n is as fast as you can do anything because you have to wait at least log n time for everyone to interact once. So if that constant is big enough, those 3 values will all be positive, even if the gap is 1, and that solves majority. But the size of that has to be linear, which is a lot of space. So now we're going to outline a quick history of this exact majority problem. So first of all, on the time axis here on the left, we'll note that you can't do better than log n time because you have to wait log n time for everyone to interact. So that's impossible. And then there was a crucial impossibility result that came from Alistar, Apsnaz, and Gelashvili, saying if you want to do better than linear time, if you want to do better than that simple 4-state protocol, you need at least log n states. And since then, there's been a series of works getting progressively better, so getting better bounds in both space and time, getting closer and closer to this dual optimum. In particular, a lot of the results took log squared time, and then there was some series of results all using log n states. But up until this work, there was no algorithm that was simultaneously optimal in both, and that's what we have in this chapter. And to sort of briefly describe the ideas behind the algorithm, it relies on this paradigm of cancel and split reactions, which is actually common to a lot of existing protocols. And the idea is going to be to think about state A and state B as having values positive and negative. In this case, I guess they're red and blue. So and confusingly, I think B is red. So we have two colors, red and blue. And the idea is the opposite colors, the opposite opinions are going to cancel out. So that's the same sort of rule we had before with the 4-state rule. But the problem is that canceling is too slow. So if we wait a little while, a lot of agents will cancel, but not all of them. So what we're going to do here is we're going to do a second type of interaction, what we call a split reaction. And that's going to say if there's an agent that's neutral, an agent is going to be able to split, and then we're going to split that bias in half. And we're going to track the bias as some value. So now we have 2 agents that have bias of 1/2 or 2 agents that have a negative bias of -1/2. So then we're going to do some splitting. And importantly, we're going to think about doing this in synchronized rounds. That's sort of the way existing protocols did this. And if you do it in synchronized rounds, you're able to then guarantee that all agents are able to split if they want to. And what this does is sort of keep spreading out the opinion until eventually that difference of 1 is split across the entire population. And now there's no blue left. So everyone can now agree that red is the majority. And if we actually synchronize that, this works. And this is an example of a log squared time protocol. So here's a simulation doing that log squared time, where here on the x-axis, we have all the different bias values. The bias values are different powers of 2. So eventually all the agents have a negative bias, and it's -2 to the -18. So 1/2 to the 18, 1/2 to the 19, and 1/2 to the 20. So we split them up and they all have a very, very tiny bias, but now they've all agreed on one side. And it's log n states because all the states are all these powers of 2. But this is too slow. So it's log squared time because we have to go through these log n state splits, so sort of 1 for each hour. And you have to wait log n time to do one of these synchronous hours. So the traditional synchronization schemes end up being too slow. Now, one idea you might have is just, what if you did no synchronization whatsoever? What if you just let all these cancel and split reactions just kind of happen for free? Well, in that case, you don't get anything good. You just produce all the different bias values all together, and you're not sort of converging to anything. And in fact, even if you waited a long time, you would not all agree. So in this case, here's a simulation where a lot of the population, all the red agents, have really big bias values. So the actual majority should be red, but all the blues happen to split faster and get ahead. So they're actually present in much bigger count, because the count here is on a log scale. So it could just not work at all. So the idea behind our protocol is to split the difference, to do some partial synchronization. So we have a novel rule for a clock. We have a phase clock rule here that uses a couple different rules of logic. One is if 2 agents have the same value, so the value we call their minute. If 2 agents are in the same minute, one of them is going to increment. And then if they have different minutes, the one behind catches up. And then using that rule, this is a simulation showing what the distribution looks like. We get this sort of traveling wave in the count of the agents at each minute. And then we're going to bin the minutes into hours. So in this case, 5, some constant number of minutes will be 1 hour. And the point of what this clock does is it mostly synchronizes the population. So we can say that most agents will all be in the same hour, but not everyone. But it turns out that partial synchronization is enough to make this rule almost work. So here's a simulation sort of representative of what it looks like. We're doing those same cancels and splits, but we're not perfectly synchronized. But what we can actually prove about this process is most agents will end up having 3 consecutive values. So here, -18, -19, -20, with the majority opinion. So here, red is the majority. So we get most of the agents correct, but not everyone. So we're most of the way there. And then the rest of the protocol and the rest of the paper goes into details about how we get from here to being totally correct, how we get everyone to agree on red while making sure there's no possibility of error. So there's a few different ideas we use. The first idea is Some agents, their value might be too big. They might have a bias that's too high. The way we solve that is we have a separate subpopulation that we've sort of hidden away that comes in to do more split reactions. So we add more split reactions, that pushes all the values down into the bulk here. And then these values here in the bulk, they're able to do cancels because they're right where the majority of all the red agents are. And then the last thing we're left with is a few straggler agents that might have really small values. And the way we handle the small values is, well, ideally, we would like agents that have a bigger bias to be able to just consume the agents that have a smaller bias. Like if my bias is 1/2 and your bias is -1/32, I should just eat you up. And if I had an unlimited number of states, I could do that. And I would just say, okay, now my bias is some different fraction. But I can't have all these new fractions. That's too many states. So the shortcut that we use is we don't actually remember the exact value. We just sort of remember, hey, I was 1/2 and I ate up someone who was smaller. So now I have some unknown range of values and I'm just going to remember that. And it turns out that actually works in the regime we need. Okay, so that's sort of some high level ideas for how we solve this majority problem. And the next work I want to talk about is sort of the other most famously studied problem in population protocols, which is leader election. And this is a different paper that's joint work with Jana Berman, Ho-Lin Chen, Shui-Ping Chen, Dave Doty, Thomas Nowak, and Xuan Zhu. And before I dive into this, though, I'm just going to take a brief breather since I've been trucking ahead pretty hard, and just if there's any questions or not. And of course, feel free to interrupt me the entire time if anyone has any questions, and I'll try to pay attention, but something like the chat's probably not as effective as just sort of shouting at me. So at any point, feel free to shout out. But yeah, if there are any questions so far, I'm happy to take them. Otherwise, I guess I'll introduce the idea of the next work. So this is leader election. This is the other sort of most commonly thought about problem. And leader election turns out to have a very simple protocol that's sort of the other most useful, interesting two-state protocol. So here's the two-state protocol for leader election, where you're going to have two states. Now we're going to call them L and F, where L stands for leader, F stands for follower. And what do? Well, two leaders meet, one of them drops out, becomes a follower. So now we have some different dynamics, has a different system. And we typically think about starting from this initial configuration where everyone's a leader. And if everyone's a leader, well, every time two leaders meet, the count goes down until we get to this configuration right here with a unique leader left. And then that can't change because the only interaction is not possible. So if we think about simulating this rule, so here's a simulation with n equals 50 agents, we can see the count of leaders actually drops down roughly like 1/t. And sorry, these curves are mislabeled. So that's the count of leaders. The count of leaders is going down to 1, as it should. But it's actually also slow. It's also linear time. And we can see that very directly because the last transition that has to happen is two leaders meeting. And for two leaders to meet, that's really rare. So that turns out to be linear time. And an easy way of sort of checking this is to think, well, from the perspective of one leader, they have to meet another leader in their next interaction. The chance of that is like 1/n. So the time it'll take for that to happen is like n. But that does solve leader election. But in this paper, we actually think about an even harder problem, which is this extra adjective here, self-stabilizing. So formally, the rule is now we want to solve leader election, but we're going to start from an arbitrary initial configuration. So if we had defined this to be the rule, then what the adversary would do is say, okay, well, if this is your protocol, what happens if this is your initial configuration, all Fs? Well, in this case, it doesn't work. You don't get a leader. So this is the definition of self-stabilizing, and it was meant to model memory corruptions. This is sort of an arbitrary number of transient faults have happened. Your unique leader dropped out. Now what do? You have to recover somehow. And this problem turns out to be really hard. So here's one thing you can prove pretty quickly, that if you possibly could solve this problem, whatever your solution is, has to exactly depend on the population size. So we will see you can solve this problem, but if you can solve this problem, here's a sort of a representative example saying, all right, if you could solve leader election, that means you could somehow reach some stable configuration that has a unique leader. And let's say the number of agents here is n. Well, whatever protocol you possibly came up with that solved this problem is not going to work for the population size n-1. And the reason is, if you take the rest of the configuration besides the leader, this configuration here could have been an initial configuration with n-1 agents. So whatever that protocol is that you designed that worked here, if you start from here, it's not going to elect a leader. And the reason it can't elect a leader is we know this original configuration is stable. So it's not going to produce a second leader. So then from this initial configuration, you wouldn't even produce a single leader. So the only way to solve this problem is to have your whole protocol depend on the exact population size. That's sort of a fixed requirement. But once you do that, you can actually solve this problem. So the simplest protocol comes from these authors a few years ago. And the idea is the states are going to be the integers mod n. And the rule is just if two agents have the same state, one of them increments. So we can visualize the protocol as all of the states living in different buckets. So here we have 7 agents in states 1, 3, and 5. So we're putting them all in sort of the bucket where their state is. And a way to visualize it is saying, okay, if 2 agents have the same state, they're in the same bucket and they meet, one of them jumps forward. And that's going to keep happening until we eventually reach the unique terminal configuration where all of the states are present. So now we have stabilized. And this protocol actually does another really nice thing. It actually solves an even harder problem than leader election. So in this case, we just called the first agent here the leader. But it actually solves a strictly harder problem of ranking. So we could view these n states as n different ranks. And once we've stabilized, well, the leader knows they're rank 1, but also every other agent knows they have some unique rank in the whole population. And this protocol has another really nice property where it's silent, where once it has reached the terminal configuration, there's no more transitions whatsoever. And that's not true in general. It could have been possible that some of these other states kept changing, but in this case, none of them did. So, and then let's think about time analysis. So that simple leader election was slow because it took linear time, but this protocol is even worse. So here's a good sort of bad configuration to start from. It's a good example where you're missing the leader and you have 2 agents in the same state up here, and then every other state you have 1 copy. So the only interaction that can happen here that'll change anything is if the 2 agents here meet. That takes linear time. And after that happens, the agent jumps forward. And again, we have a single collision here that we have to wait for. That takes linear time. And each of these steps takes linear time. And there's n of these linear time bottlenecks, which means you wait n squared time for this to finally finish. So that's really slow. If n time was too bad, if linear time is too bad, quadratic time is way worse. But that's the existing protocol. And in this work, we sought to determine, are there any better protocols? Can you do faster? And you can, and we found sort of 2 different competing protocols that have a bit of a trade-off. The first one uses the same amount of states asymptotically, so order n states, and it drops from quadratic time down to linear time, and it's also silent, which turns out to be, this is actually the optimal time for a silent protocol. Then our other protocol is much faster, so it gets all the way down to log n time, but it uses a lot of memory. It uses exponential states. And both of our protocols actually solve that same ranking problem. So when they finish, the entire population has unique ranks. And for both these protocols, one of the key ideas behind how they work is a reset subroutine. And this actually comes from a DNA paper. And the paper here was trying to solve a different problem of detection. They were trying to detect the presence of a molecule. But it turns out the analysis here sort of also applies to this reset subroutine, where the idea of the subroutine is if an agent wants to trigger the reset, so here we have everyone in state 0, they're going to set some variable reset count, and it's going to get pretty big. It's going to be on the order of log n. So here we have some agent, we say like they've detected some error, and they've realized that they want to tell everyone, hey, we need to reset, we need to choose new values. So how the rule works is when 2 agents meet, they're going to take the max of the 2 values, but it's the max minus 1. So if the 10 meets a 0, they both become 9. If a 9 meets a 0, they both become 8, and so on. And you can prove a few things. You can prove that this positive signal, the values being positive, spreads to the entire population. So it looks like an epidemic, and that spreads in log n time. But then later on, but also in log n time, it decays back to 0. So it does sort of both things you want. It tells everyone to reset, but then everyone all resets quickly. Then the key time bottleneck that we have to overcome in both of our protocols is detecting rank collisions. So that existing protocol, the reason it was so slow is it maybe had to wait for up to n direct collisions to happen. Our linear time protocol, the one that's faster, is faster because it only has to wait for a single collision or a constant number of collisions. And the idea is once it detects one of these collisions, it does this reset protocol, it does a global reset, and it tells everyone to choose new values. And when everyone eventually sort of gets to the unique, and everyone is stabilized, you've only had to detect a collision once or maybe a constant number of times. But if you want to do any better, right? If you want to do faster than linear time, you have to be able to detect these collisions even quicker. So one of the key problems we need to solve in this work is how do we do fast collision detection? And to warm up that idea of fast collision detection, so what we're ultimately going to have is going to be optimal time, log n time. But it's easier to see the idea if we sort of start by just taking one step ahead. So rather than linear time, we're going to jump down to square root of n time. And here's the idea of how you can do that. So linear time is how long you have to wait for two agents to interact. So here we have two agents have the same state. They're both duplicates. They're both state 4. We need to learn that there's a collision. But if we wait for them to interact, that's linear time. So how could we possibly do that faster? Well, one idea is to observe that it takes linear time for them to meet directly. But here's something that's going to happen quicker. Something that's going to happen quicker is this agent 4 is going to meet some intermediate agent. Say they're in state 7, some arbitrary agent. And then that agent is going to meet the duplicate 4. And if you actually compute how long does it take to wait for some agent to happen to meet both of these 4s, that'll first happen quicker. That'll happen in square root of n time. And we're going to try to use this to somehow detect the collision. So somehow agent 7 needs to observe that these two 4s were not actually the same. But we have to do it in a self-stabilizing way. So the idea behind how we do it is in every interaction, the agents are going to pick some random sync value. And they're going to keep doing this forever, which is why it's not silent, by the way. So in this case, if agent 4 meets agent 7, they're going to agree on some random sync value. Here it's 132. And they're going to locally store this. So they're going to have some local data structure in their memory. And agent 4 is going to say, OK, I met 7. We agreed on 132. Conversely, 7 says, OK, I met 4. We agreed on 132. And what this does is now when agent 7 meets the other agent 4, well, now it can say, hey, I met a 4 before. I met agent 4. We had the value 132. You agree, right? And this agent 4 says, wait, what? I don't have that value. And that's an inconsistency. And that's actually how they're able to indirectly detect a collision. And you can show that this actually sort of works exactly as you need, and it lets you detect collisions in only square root of n time. And then you trigger the reset. So then you do some reset protocol, and then you do the rest of whatever your whole protocol is to get everyone to have the unique ranks that you want. Then it turns out we can iterate that idea, and we can actually get collision detection in optimal time, in log n time, if we use an even more complicated data structure. So the first idea is going to be the same, right? So we had sort of a representative example. Agent 7 met agent 4, and they shared the value 132. But we're no longer going to wait for 7 to meet 4 directly. We're going to have a much longer causal chain between these two duplicates. And the idea of what the protocol is going to do is it's going to say whenever two agents meet, they're going to kind of share this entire history. So they're going to have this tree where what happens is they're going to share all the data they've seen before. They're going to agree on a new sync value. So now they have the sync value 99. And they're going to put that sync value in their tree. So now say agent 2 here knows that they met agent 7 who met agent 4, and they shared these appropriate values. And that's going to keep going. We're going to keep iterating on that idea. And then eventually there's going to be some agent all the way out here, agent 6. And agent 6, again, they've heard from agent 4, but their agent 4 is really deep down in this causal tree with all these sync values on each of the edges. But what this now does is when agent 6 meets agent 4, it'll be able to detect a collision. And it turns out you can prove that there's going to be one of these causal chains from 4 to the other 4 that's going to form in only log n time. And the length of the path is also on the order log n. And once this happens, then you're going to be able to detect one of these collisions. And the reasoning is similar. The reasoning is, well, this agent, its tree is so deep, it's able to record all the history going back to knowing that there's a chain of events where it heard from someone who had the identifier 4. And then it meets this other 4, and the other 4 basically has no corroborating information. It's not able to sort of match any of these sync values, and that's an inconsistency that, again, lets us do a reset. So that's how that was one of the key challenges we had to solve in that problem, and one of the things I sort of found most interesting in retrospect.
I have a quick question.
Absolutely.
So when you do or when you're calculating the sort of runtime for this, is there any taking into account some sort of like the amount of time that it would take to like build these trees? Because as the trees get deeper, it's going to take longer to.
That's a good question. No, so the population protocols model, like a lot of models in distributed computing, it assumes the computation, the transition function between the two agents is instantaneous.
Okay.
So it's really a model of like the communication and the interaction. And well, in the original model, the memory was so limited that that sort of made a lot of sense. Here, the memory is bigger, but sort of still you're sort of modeling that as it instantly happens.
Okay. Yeah.
And that's actually a really good segue into the next topic, where we're going to focus more in the guts of how the model works. So this is some new notion we introduce of message complexity, and this is joint work with Tali Amir, James Opsnez, Dave Doty, and Masa Eftekhari. And the idea is, well, we've been talking about some protocols, including these last ones in this talk, that have a lot of states. And if you have a lot of states, that's going to increase the communication cost. So there's actually two things. So Daniel was already thinking about what about sort of that cost of the internal computation and the internal storage. But the thing that we're focusing on here that we think is maybe an even harder cost to pay is the fact that in this model, when the two agents interact, they basically share their entire state with each other. Because more formally, we say, oh, there's some transition function that takes both states and decides what to do next. So the idea was to say, well, that's a lot of communication if you have to share your whole state. So we're going to introduce a refined model that actually distinguishes that communication complexity. So more formally, we now say the state of an agent, Q, is the combination of a message, M, and an internal state, I. So here we have sort of an arbitrary representation of two agents. Here their messages are supposed to be simple, so they're just colors, red and blue. Their internal states are more complicated, these big bit strings. And now the idea is when they interact, the transition function that updates them, updating the agent on the left, all that it can see is the internal state, the message, and the message that it received. Conversely, the agent on the right can only see the blue message. They're no longer sharing their internal states. And the original model, so some of the original simple protocols, the number of states they used was always constant. It was a constant number of states, irrespective of the population size. So that by default means the number of messages is also constant. But most of these recent protocols that use big states, including the majority protocol and the leader election protocol that I talked about earlier, they use big states, so omega of 1, so super constant, but they also use big messages. So like if you think about, say, that averaging rule, when the two agents met, they shared their entire integer. They shared all their information. So the idea of this paper was to say, well, what if we still allowed the agents to have big internal memory, but we bound the amount of communication, which is sort of this natural mathematical intermediate. And it was also sort of well motivated by thinking, well, maybe your model, maybe you're able to actually add more memory, but maybe the communication is the hard part. So what can you do in that regime? And well, here's some examples of things you can do. Here's some of the fast protocols that we developed and analyzed in this paper. The first is solving a problem which is a generalization of leader election. It's called Junta Election. So we don't need just one leader for this. We need a small size, we're going to call it a junta, and the number of agents in the junta has to be at most square root of n. And it turns out that if you can solve this problem, you can do a lot of other stuff. So junta election turns out to be the key thing that you need more states for a lot of the state-of-the-art leader election and majority protocols. And the idea of our junta election is we're going to have some internal variable we call the level, and the level is going to decay doubly exponentially. And what that means is the maximum level that we expect to see in the population is going to be about log n. Also, you can show that the number of agents who have the biggest value of the level, that's going to be at most square root of n. So here's a representative example. We have the max level is only 2 in our small population. And the thing that we would like to do is we would like this agent to know that they're the max, they're in the junta, and everyone else needs to learn that they're not the max, they're not in the junta. Now, if we had a lot of messages, if we could just broadcast our whole state, we would just broadcast whatever our level was. That'd be easy. But that uses too much memory, too many messages. And we're actually going to solve this problem with only a single message. So the message is only a single bit. So you have 2 different states you can be in for your message. And the idea of how we do that is we're going to rely on timing and internal counters. So every agent is going to have some internal counter represented by this line down here, and they're going to count how many interactions they've had. And then their messages are 2 messages, stop and go. So if their counter's in one of these green regions, they're going to broadcast the go message. If they're in one of these red regions, they're going to broadcast the red message, stop. Then there's going to be some special locations at the end of the red regions. We're going to call them doors. So these are the values at these door locations. And the rule is you keep counting, but if you're at a door, you only keep counting if your level is higher than the door. So in this case, if your level is 0, you stop. But if your level is 1 or higher, you keep counting. But if you've stopped at the door and you see a go message, well, you go. That's the idea of the go message. So in this case, some agents proceed forward and bring everyone else up. Then we get to the second door here, D1, and at this one, only the level 2 counts forward, but it brings everyone up. Now, in reality, this might be very asynchronized, and they might be totally out of whack, but we're able to prove that once you get to the last region here in the last door, they're all synchronized and they all get stuck together. There's no green signal left, and now no one has a bigger level, so everyone learns 2 was the max. This agent knows they're in the junta, everyone else knows they're not. And here's some simulation data that confirms that. So here's a bigger population where the max level was 6, and everyone learns that, everyone gets stuck at door 6. Now, another problem that we solved that I thought was pretty interesting for the model was exact size counting. And this is actually a really nice problem to think about for the model we have, because the agents have a lot of internal memory. So it makes sense to talk about size counting because they have enough memory to store the value n. But they didn't necessarily need large messages to do counting. Maybe we can do counting with a small number of messages. And in particular, we need to do it quickly. So it's also worth observing, it's actually pretty easy to do counting slowly. And the rough idea is you think about every agent holds a token and they pass their tokens around. And eventually you're going to leave with one agent who holds all the tokens, and they're going to have some count of how many tokens they hold. So there's like a really simple protocol you can describe that does that. It's just really slow. So we were trying to think, can you do fast exact size counting? And our protocol uses a leader. So like many protocols, having a leader sort of gives us some nice synchronization. So we're going to sort of assume that using other protocols, we've somehow given ourselves a leader. And once you have a leader, the idea of how the protocol works is we're going to think about the leader as having one unit of some sort of mass. So in this case, we have 7 agents in our picture. We have 1 unit of mass held by the leader. And our goal is to, again, do a sort of averaging, similar to our majority ideas. So we would like to average this mass among the entire population. So how are we going to do that? Well, we don't have a lot of messages. In this case, we're only going to use 5 messages here, and they're going to be 0 through 4. And we're going to think about them as units of weight. So right here at the beginning, the message 0 is saying you have 0. And then all these intermediate messages are values 1/4, 1/2, 3/4, and then 1. And then what we do is we do averaging. We do that same sort of discrete averaging rule. So if a 0 meets a 1 or a 0 meets 4, they're both going to become 2. 0 meets 2, they both become 1. And the key important feature here is when you do this averaging rule, you very quickly get all of the values to be 3 consecutive values. So it's either going to be 0 through 2, 1 through 3, or 2 through 4. And then once you have 3 consecutive values, the agents can then broadcast, hey, what values are out here? And they're all going to learn that the values are between 0 and 2. So then they can sort of zoom in and update their interval and say, okay, great, we were 0 through 2, so let's redefine the interval now. And now they've all learned that they're in the interval between 0 and 1/2 without having to actually share all that information. And we keep doing this every round. So now for the next round, we're going to do the same averaging. And the key point is this interval you're in keeps shrinking. So it keeps shrinking every single round, gets smaller and smaller, until eventually the interval is so small that there's only one possible fraction that lives in it. So in this case, we've gotten to a very, very small interval. It's now powers of 128. So it's these dyadic rationals. And now we know, well, there can't be 8 agents and there can't be 6 agents because the interval doesn't contain those. So now everyone knows there has to be 7 agents, and they can all stop and say, great, we're done. We've counted it. It's 7. That's sort of the high level idea of how we're able to exactly count the population. And it turns out to be pretty quick. So this is log squared time, because it goes in these synchronous rounds. So we use one of these existing phase clocks. Every round of the phase clock needs log n time. And the number of total rounds you need turns out to also be log n. It's how many of these divisions you need to do before you get over on one of these intervals. So this turns out to also be log squared time. And it's sort of a fast counting protocol. Then one of the other big parts of the work is we think a lot about computability. So we think a lot about, if you don't care about time, just what can you compute at all? And here we're a lot more strict. Here we actually want probability 1 computation. So you can't just be with high probability. You have to be stably computing whatever function you want. And we're restricting the messages, but we're letting the internal states grow. And we actually get a pretty complete picture where if your number of internal states is sublinear, if it's scaling less than n, it turns out you're limited. You're limited to the class of what's called semilinear predicates, which is exactly what the original model could do. The original population protocols model with constant states and constant messages, you're no more powerful. But then once you get to have a polynomial number of states, you can actually simulate a Turing machine. So it's sort of as powerful as you could hope, and you could sort of use all of the memory of the population to be a big Turing machine tape, and you could sort of do whatever you want with that. And then we even show beyond that, if you're willing to go to all the way to unbounded states, you could actually do the same Turing machine simulation, but you only need a single bit of messages. So you can actually do sort of the minimal possible size messages and still sort of do some sort of Turing machine simulation. Okay, and I'll think again, take a pause with all those new ideas. And there's sort of one more work I'm going to describe, which is a slight variation from the population protocols model to think about more general chemical reaction networks. But again, I think this is a good place for a brief breather, tongue twister, before we go into the last chapter. So any more questions from what we just saw? Okay, and this one's going to be a quicker flyover because the model is slightly different. And rather than sort of diving into the technicalities, I'm just going to sort of give the high level idea of what we do and how one of our key open questions was then resolved. So this is joint work with David Doty and David Haley. And let's sort of just get the flavor of what this project was about. So this is talking about more general chemical reaction networks. So for a population protocol, it had to be 2 agents in, 2 agents out. But now we're going to consider more general reactions that maybe change the number of total agents here. So here, the number of molecules, agents / molecules is going to change. So here's a really simple reaction. X goes to 2y. So let's imagine sort of starting in a configuration that has 3 X molecules. What's going to happen? Well, eventually they're all going to convert to 2y, and we're going to get 6 Ys out. Okay, so that's not particularly surprising, but what we're going to do is we're going to think about this as computing a function. So, well, what function should this compute? If we start with 3 and we get 6, well, it's going to compute the doubling function, f of x equals 2x. So because we're allowed to change the counts here, we can compute functions in this new way, compute functions that change the total count of the configuration. And we can compute other functions. So here's another slightly more complicated example. Now we have x1 plus x2 goes to y. So if an x1 meets an x2, they combine together, they become this new species y. And now we're going to call x1 and x2 here the input and y the output. So for example, if you start from 5 x1s and 4 x2s, well, we're eventually going to get 4 y's and 1 x1 left. And more generally, this function here, we can formally say computes the function min, because whichever one of these 2 species here is the minimum, they're going to be limiting. They're going to be the limiting reactant, and all of them will get consumed and will produce that many y's, and the other ones will be left over. So here's 2 simple examples of the type of thing we're talking about in this work, which is computing functions. And again, this is discrete, so these are integer valued functions in this model. And we have this notion of stable computation, which intuitively just means it has to be correct with probability 1. And the goal of this paper was to think about function composition. So here we have our 2 simple CRNs, the min and the doubling CRN. And we're thinking about, well, what if you had these 2 CRNs and you wanted to mix them together? So we're going to compose these 2 with each other. And the way we're going to do that is we're going to rename the output of the min CRN. We're going to call it W. And we're going to rename the input of the doubling CRN and also call it W. And to get one big CRN. So we sort of took these 2 things, we mixed them together, and we got this 2 reaction system where x1 and x2 both become W, and then W becomes 2y. And it's sort of hopefully intuitive and pretty easy to show formally that this will now compute double the min, because eventually you'll produce exactly the minimum amounts of W, and those will all double, and you'll end up with exactly what you want. So this works. But the interesting part of this work was realizing this doesn't always work. So I talked about min, and if I mention the min function, you might naturally wonder about sort of its cousin, the max function. And turns out you can compute the max function. It's not nearly so simple, though. And this is the simplest CRN that actually does it. I think people in the audience actually proved that formally, that you need this 4 reaction CRN. But once you have it, this is actually going to stably compute the max function. It's less obvious though, less easy to see. But the idea is, well, the first reaction here is going to produce x1 copies of the output, and this one's going to produce x2 copies of the output. So those two reactions are going to sort of give us the sum. And it turns out that the max function is equal to the sum minus the min. So what we do here is we have z1 and z2. They're going to sort of be extra copies of the input. And then they do that min reaction. They meet and become a d. So the amount of d's we produce is going to be the min. And then d's eat up the y's. That's how we're doing subtraction here at the end. So you can actually prove this CRN stably computes max. But it doesn't work in this nice composition scheme. If you try to then plug in the output, if you try to call the output here W and plug it into some downstream CRN that tries to do doubling, it's just not going to work. It's not going to stably compute anything. And the idea is that these bottom two reactions compete. So sort of all of the W's might jump into this reaction and you might get a lot of D's left over. And then you sort of are not going to have some unique value. So there's no guarantee that you're going to produce some deterministic amount of Y's in this CRN. So it doesn't work. And the reason it's failing is because we took the output, Y, and we tried to plug it into another reaction somewhere else. So the thing that we did here that is sort of the problem is it's not what we're going to call output oblivious. Whereas this min CRN is nice because we never used the output species, we never used it to be an input. So it is output oblivious. And the idea was to say, okay, well, when you're output oblivious like this, you have this nice mode of composition, and that's sort of a naturally motivated property to have. So we were then asking our question of, well, what are the output oblivious functions? What can you compute in this output oblivious way? So that was the main question we were asking. And these are integer valued functions. So we're talking about integer valued functions that you're computing in this CRN model. And again, the idea of being output oblivious means what functions, there has to exist some CRN that's going to compute it in this output oblivious way. And again, the motivation we had for all this was modular CRN design. If you had all these output oblivious functions that had output oblivious CRNs, then you could take any of these output oblivious CRNs, you could mix them together, and you could get all the composed functions. It would give you some sort of toolbox. And, or just more formally, it was some class of functions. So purely mathematically, it was like, all right, well, what functions could you do? And previous work has classified all the functions you can do in the original CRN model. So that was already well known. And we had some subclass here. So we were trying to identify what that was. And actually, the start of this work was this impossibility result. So actually, Dave mentioned me solving a problem in his class, and it was this problem. It was actually this exact question: can you compute max? It's easy to see that this CRN is not output oblivious. So this CRN does compute max, but it breaks the rule here. It eats up the output. But that doesn't mean there's not some other CRN that does it. And the other CRN could maybe be big and complicated. It could maybe even use one of these leader species like we've used before. You could start with a leader. We're going to give you that power. But you can actually prove that it's impossible. No output oblivious CRN, even with a leader, can compute this function. You can't possibly compute max. And the start of this project was actually figuring this out and proving this. And then that led to this natural question of, okay, if you can't do max, well, what can you do? What is this function class? And we gave an exact characterization, but rather than 1 hour in throwing a bunch of symbols at you, I'm just going to do, here's the picture of the theorem. So here's a sort of representative example of one of the functions in 1D. So a function from n to n, so a one-dimensional function. And the key idea is that it has this sort of periodic staircase behavior where for a while it'll do something, but it always has to be non-decreasing, so it can only ever go up. But then eventually it's going to repeat itself. So it's going to be non-decreasing and periodic like this. And that's sort of the general picture. Every function will look like this. And then our full theorem, though, is in arbitrary dimensions. So it's not just the one-dimensional version, but it's captured very well by just looking at the two-dimensional picture. So here's a representative example of the two-dimensional version of this function class. So in one dimension, we have these periodic staircase shapes. And if you actually take the graph of this two-dimensional function, and you sort of stare at one of the lines here, it actually has the same shape. It has sort of a periodic staircase thing going on. But then the more interesting behavior happens when you look out here. You look at big values of x1 and x2, where in this case, we have these sort of three different kind of bumpy quilt regions, I'm going to call them. And more formally, we have some definition we come up with called quilt affine. that describes what this bumpy quilt behavior is. But the key idea is that we have this sort of bumpy quilt behavior in this big patchwork where the way these quilts are sewn together is we're taking the minimum of a bunch of these bumpy quilts. So that's the very hand-wavy pictorial version of a tedious and technical sort of formal proof we have. It's not very clean to state, but here's sort of the high-level idea of the picture. So it's these things we call quilt affine functions. But one of the nicest results that actually came out of this that I liked a lot was if you took our function class with one of these representative examples, and you did basically the process of zooming out. So if you did the mathematical equivalent of stare at this picture from 1,000,000 miles away, it would look like this. So all the quilt parts would smooth out to these planes. And the thing you would get would exactly belong to the function class that came from a previous paper that thought about the exact same question in a continuous model. So in some sense, the results we had based on the discrete model end up lining up. They're just a lot messier because you don't have these nice clean planes. You have all these annoying bumps. So with all the technicalities swept under the rug, I sort of really like this as one of the big conclusions. But our paper actually left a really key open question, which is that we relied on a leader. So we showed that even though you have a leader, you can't do anything more. But all of our constructions, when we sort of said, hey, here's a CRN that does something, all of our CRNs had the power of a leader. And if you don't have a leader, there's another constraint. It's this notion of being super additive. And we were able to actually classify the dimension 1 case, but there was a huge open question, which was for the more general result, we still couldn't prove what you could do with a leader. But we had a conjecture. We thought that there was one extra property to staple on to our main theorem. But that we were not able to resolve that until recently. Some other authors, including Anne here in the audience, Ben Chug, Ann Condon, and Human Hashemi, did actually show that that is correct, made it a theorem, and actually ended up with a much nicer version of our main theorem statement as part of that on the way there. That's something I was really happy to see. It's really cool to see like someone help resolve that sort of open question that was left. And I want to finish by just saying thanks to all of my many, many collaborators. They made this whole PhD process much more enjoyable, and I don't think I would have wanted to do as much research if it was all by myself. It would not have been as fun. And thank you all for your attention, and I would be more than happy to answer any questions now at this point.
Eric, yeah, first, it's a great talk.